Welcome to day 12 of the Advent of Code 2022 in Rust. So today we're dealing with a hill climbing algorithm, or so we're told. So we've got our communication device. It's not working because we're too low down. We're trying to get to high ground where we can use the device. And we're given this terrain map, which has letters A through Z, which tell us how high or low the terrain is at that point on the map. We start at the point S, which is actually A, that's the elevation of it, and we end at E, which is actually elevation Z. And we're allowed to move up by 1, so moving from A to B would be fine, moving from B to Q would not be fine. So allowed to move to 1 letter higher at most, but we can go down as far as we want. So we're told to find the shortest path from S to E. So we should be thinking something like a grid search algorithm, and in particular, if you've done any kind of games programming, you'll be thinking about the A-star search algorithm. So that's what I'm going to use, and let's jump over to Wikipedia, where it tells us all about it. So Wikipedia has some helpful pseudocode that'll walk us through exactly how the algorithm should work, although a few details are hidden. The better way to think about it is just to look at a visualization of what this is doing. So if we look at this, we start from a starting point, we're trying to get to an ending point. We consider all the green squares to be open, those are squares we still want to search. The red squares, we know how much work it takes to get to those. And we're constantly trying to pick out the ones that are most likely to take us towards a sensible endpoint. So to that end, you use an H function, which tells you what's your best guess. How far is it to get from the point you're currently at to your endpoint? So that's just really any function that gives you a measure that when you're closer to your endpoint, it's smaller. When you're further from the endpoint, it's larger. So it kind of guides you towards your endpoint. We keep track of all of the nodes we haven't yet finished considering. We keep track of all the best paths so far. We keep track of the amount of score that it's taken to get this far so far. We keep track of how far we think it is from each node that we're currently working with to the end, so from the red squares. And then we loop through looking for the best node that's most likely to give us a good chance of getting close to the end. We take that out of our working set. We run through all the neighbors of that, so all the things that are valid according to the rules of our game, or the rules of our search. We use this distance function to say how much work is it to go from the current square we're on to a neighboring square. So this isn't really relevant to us, but it's something that you might care about if you had tiles with long grass on in a video game, for example. And then you update your positions if that neighbor is a better option for getting to the end than the current path is. That's pretty much it. I've implemented this already because it's quite a bit of code and it's not very interesting to watch, especially when there are lots of implementations out there, there's pseudocode out there. So what we're going to do instead is go in and work out how to customize this search algorithm to give us what we need to solve the problem. Just to quickly recap the code that's already here then. The first job is to load up the input file, and we do that by converting it into a map of grid coordinates and heights, and we handle the S and E, the start and end, as special cases. So S becomes 0 height, E becomes 25 height, and everything else is normalized as its ASCII value from 0 through to 25. So then the next thing to do is to have a look at the A-star search. That's this function here. And this is pretty much just an implementation of what we just saw on Wikipedia. And there are a few things in here that need customizing. So if we start at the bottom and have a look at the H function, so this is our cost. So how close do we think we are to the end? And we're being given P1 and P2, where P2 is the target node, P1 is the current node. So this can be done with a Manhattan distance. So we'll say how far is the row of P1 in absolute difference from the row of P2. And then we can do the same thing plus P1.1 and P2.1. So we're saying what's the difference between the rows, what's the difference between the heights, absolute difference. So we throw away any negative numbers, just make them positive, add those together. So that's a very simple distance function. Then we want to check if a move is valid. So this we do by checking if the tile we're trying to move to is in our grid. That's the first thing we need to worry about. If the grid contains key, move to. And also it follows the rules of our game. So if we do grid.get the height at that move to node and unwrap that, that should be less than or equal to the height of the node we're currently on plus 1. So that's given by the puzzle input, or by the puzzle rules even. So that's those two things sorted. The next thing we care about is this distance function. So for us, we don't care about this. There's no cost difference between moving from one square to any other. So we do need to track it though, because that's how our algorithm knows that we've traveled somewhere, what distance is best, which way to go. So we'll just say moving from one grid square to another has a cost of 1. And that's then helpful, tracking that as distance 1 for each move, because it means that at the end, when it comes to working out the length of our path, that must just be the number of nodes that were required to be visited to get to the end node. So we can do that by looking at our past costs of all the things we've traveled through. We will get the past cost for the end node and unwrap it. And that should be the total distance to our end. We just need to dereference that, and that's a usize then. So those are all the customizations. Let's now go and run this. So we'll kick it off with cargo run. And I've modified the program today so that it'll take the file to use as an input. And this is the input that we're given as part of the puzzle, the one that we know the answer to. So it's saying the answer is 31 steps, which is right. Now let's have a look at what this is printed out for us. The first thing it's printed is the puzzle output. So you can see we've got the starting point at the top left, so 0, 0, and the ending point 2, 5, which is row 2 indexed by 0 and column 5 indexed by 0 as well. And then the first thing it'll consider is the starting point, and it finds two neighbors. One is 0, 1, the other is 1, 0, both with height a. So that's the a to the right, the a down one. So those are the possible things to move to next. Then the next thing it considers is 0, 1. So that's row 0, column 1, so moving along one to the right. And that then looks at 3 more nodes from there, which is going left, down, and right. And it ends up with possible neighbors being added for all of those. So if we have a look back at this, we've moved 1 to the right to this A here, and we're saying that the B to our right is valid, the B down from us is valid, and the S left of us is valid. It won't move back because the cost to move back to a node you've already been on is higher than it was to just get there in the first place. So the conditions in the algorithm sort that out. So our possible next from that one would be B or B, going here or here. And then we'll go back through and consider the A, the B, and the B. That's then our working set. And if I'd implemented this properly, using a min heap, it would prioritize which one to go to next, which would help in terms of how much work we have to do to find the right answer. But for now, this is working, and we've got a search algorithm that we think should perform on our full input. So let's give that a try next. So if we run this against the real input, it's going to take a bit of time because it's printing out so much information on each loop. It's actually quite fast. We're just going to wait for it to end. And eventually it gives us back 472 steps to get from start to end. So let's see if that's the right answer. Okay, let's give it a check. And that's right. So we're on to part 2. Part 2 is asking us to vary our input. So rather than just starting at S, we're allowed to start at any elevation 0 point on the grid, so any A letter. And we're being asked to find how far it is from that starting point to the end point. Across all of those possible routes that we could take, what is the shortest? So fairly simple extension of the first problem. Let's jump back into our IDE. So if we take our grid, take a copy of it, and create an iterator. So I'm going to copy it because I need to reference it again in a second. Then we can filter out the grid, looking for any point on the grid that has 0 elevation. So we don't care about what point we are at the grid, just the current height, where the height is 0. Then we can map each value. And now we do care about what point we're at, but not the height anymore because we know they're all 0. And then we can call the A star search. This is where we need to reference the grid again to pass it in here. So we don't want to have moved it. Pass in the starting point, the ending point, and our H. Then we can ask for the minimum of all of those. Unwrap it, it's optional. That'll be our min value, which is a usize. Usize. And then we can print that out as the result. So definitely a brute force approach this. So we're doing a search from lots of points on the grid, but we know that our algorithm is going to inspect some of the intermediate points as we go. So we could have reused the output of our search as input to the next search. So we could definitely make this more efficient, but as a correctness part of this solution, this is certainly valid. And now that I've removed all the printing from the search, it runs really quick. So let's give this a check. Let's start by running this on the sample input. And that's giving us back 29, which is the right answer according to the problem page. So let's run it again with the real input. And we're crashing. So this no path found panic is a case I put in to handle there being no route from the starting point to the end. So that must mean that there are some A's on this grid that you cannot finish from. So let's go and correct the code so that it's optional to find a route. So we're going to want to change this usize to be option usize. So if there's no value, it's no problem. Then when we succeed at the end of our run, that'll be a sum of the value, how far the route is. And then instead of panicking, we'll just return none if there was no route. So we need to update our code up top. So the old part of the solution to part 1, we need to unwrap. We know that's always going to be there, that's fine. For this one, we need to handle this case now, so we can't ask for min over options. So let's filter these where the result is not equal to none. And then it should be safe to unwrap each of those. So we can map that result r.unwrap, because we know those will all be sums, and pass it through the min. So a little bit untidy, but let's give that a check. Let's quickly run that again with the sample input, just to make sure we didn't break anything. Coming back with 29, that's good. Let's run it now with the real input and see what happens. So not returning immediately. Let's give that a chance to run. Okay, so that took about 35, 40 seconds on a pretty powerful machine. So definitely not efficient, but let's check if that's the right answer. So are we right? Excellent, we got it. So not efficient, we could definitely have made that faster, but we certainly got it, so that's the main thing. We're nearly halfway through the Advent of Code now. I hope things are going well for you, and I will see you tomorrow for day 13.